Alright everyone, in this video we're going to talk about graph reductions a little bit more than in class. So recall, a graph reduction is when we use an algorithm for one problem to solve another. Specifically, we're going to be using a graph algorithm. And we're using it as a black box, and what that means is you're using the algorithm as is. Someone gives you the code, you just plug in your input and run it. You can't change the code or the pseudocode as is. You can't even look at the pseudocode. So it doesn't matter how the code computes or how the algorithm works. All that matters is it does what the specification says it does. So in particular, what we're going to do is we transform the input of our problem into some kind of graph, and then we apply the standard graph algorithms we've seen in class. And usually when you do this, a good set of things that you should specify are what are the vertices, what are the edges, and are they directed or undirected? If the vertices or edges have, say, weights or lengths, if so, what are they? What problem specifically are we reducing to? So maybe it's like a shortest path problem. Maybe it's just a search problem, like is there a path? Maybe it's something more complicated, like is there a cycle? Then what algorithm are we going to use to solve that problem? Sometimes we even need to modify it slightly, like we run whatever for search, and then the things that aren't marked, maybe that's what we want to return. And then lastly, we have to analyze the running time of the algorithm, including the time it took to build the graph, because remember, the graph isn't actually input, it's something we've constructed to model how to solve our problem. So the original input might be, say, an array or some other structure. In particular, our running time should be a function of the original input parameters. So we wouldn't want something like O of v plus e. That's not helpful. We'd want something like O of n squared m, where n is maybe the size of an array, m is some other quantity, but they were in the original input. So these are original input parameters. So that's the general template we'll follow, and we'll see a couple of examples of this. So to start, we're going to go back to Snakes and Ladders, but instead of playing the game, we're going to have a whole tournament of people playing the game. And in particular, we're going to have n players, and we'll have m total games. And for each individual game, there will be 3 players playing the game. And after every single game, you know the ranking of each player in that game. So maybe player 1, or in this case, player I, they did the best, they got the highest score, so they're ranked 1. Then second place was player J, third was player K, or maybe player J was first, and so on. So you can come up with this 3-player ranking for every single game. So that's this constraint here. Now, every player does not have to be involved in any game. And in total, our goal is to create a total ranking of all players. So you could think of this as you have some tournament, a video game tournament, and you want to say who is the best player at the whole tournament overall, not in any individual game, but over the sequence of games. So that's what we want to do, figure out a total ranking of everybody, 1 through n, with the special property that if player A ranked better than player B in any individual game, then A must rank better than B in the overall ranking. So in general, this would look something like, for specifically the ranked 1 player, well, the ranked 1 player can never lose. If the ranked 1 player ever lost, then they could not, it would contradict this order, because that means there exists a B that beat A, and so B should have been higher in the overall rating. So in particular, these orders don't need to exist. They're a very strong It's a very strong thing we're requiring here. So it might not exist. So in particular, what we want to do is create an algorithm that produces this overall ranking or reports no such ranking exists. So in that example where the ranked 1 player, if nobody beat everybody, or at least has never lost, they could never be ranked 1. And that would be a condition where we would want to report none. If every player loses at least once. Okay, so that's the setup. Pretty clear. So the key thing here is we're given all the individual game rankings, and we want to create the total ranking. And the key restriction here is that if player I beat player J in any game, so if there exists even a single game where player J was better than player I, then PI should rank higher than PJ in the overall rankings. And we're going to use a simple assumption for the input. This isn't important, but just so that we're clear on what our input representation is, we're going to assume the M games are represented as a list, G, where GI is a triple, P1, P2, P3, which is saying this is the number 1 ranked player in that game, I, this is the second ranked player, and this is the third. So each of these PJs is the index of one of the players. So maybe this is index 4, saying player 4-1. This was player 2. This is player 10, for example. So this would say player 4-1, player 2 was in second place, and player 10 was in third place for game I. And here's a visual representation. So maybe these are the 3 games. There are a total of 3 games and 5 players. And we could say in the first game, 5 was ranked 1, 3 was ranked 2nd, and 4 was ranked 3rd. So you could represent this as inequalities by saying 5 beats 3 and 3 beats 4. So that's just another way to phrase that. It's basically inducing a dominance relation. So this is a dominance relation. So it's a binary relation, like less than or equal to, that tells you which player was better than the other players in a specific game. And similarly, we have these. Now, given these individual game rankings, here's one potential total ranking. So 5's at the top, which makes sense because 5's winning a lot. Then we have 4, 2, 3, and 1. Now, this ranking would not work because we put 4 above 3. However, here's a game in which 3 beat 4. So if there exists a game where 3 beats 4, 3 would have to be before 4 in the list. So here's a different one where 3 is now in front of 4 in the list, and this one actually satisfies the properties. So 5 beats 2, and 2 never beats 5, so that part's fine. 3 never beats 5 or 2, so that's fine, and so on and so forth. So this is the type of ranking we want to output overall if this was the input. Okay, so how are we going to do this? We're going to use a graph reduction. So what's our graph here? Well, naturally, the vertices are going to correspond to games. So we'll have the vertices be M. Actually, we'll have the vertices be N, the players. So one vertex per player. Because it's the relationship between the players we care about, not the games. Then for the edges, we can have an edge I to j if I was greater than j in any game. So in other words, if there exists even a single game where I beat j, I was greater than j in the order, then we'll put the edge I to j, which essentially says I beat j at least once. That's another way to think of it. In at least one game. And notice by this definition, it's possible that, most real-world players aren't consistently dominating. Usually they'll lose here and there. So it's possible in this graph to have player I beat j once, but also player j beats I once. In fact, you could have I beating j many times, like 100 times, but j just won one time. But even so, if j wins even one time, then we'll have both edges. So it'll form a cycle. And if we have a cycle, we can never make this kind of ordering. Why is that? Well, obviously, if we wanted to put I first, if we put I, then j in the final ranking, if we did that, well, we'd have a contradiction because the assumption says if we ever have j is greater than I, then in the final ranking that has to be true. So this wouldn't work because there exists a game where j beats I. And so if we ever have a cycle in this graph, we know for sure no ranking is possible. No ranking with this property at least, this key property. So again, it's a very strong condition. We need players to basically completely dominate their competition for this ranking to really exist. It's a very clear ranking. No one can argue with it. Okay. So those will be the edges, and they're clearly directed. Now, what's the problem we want to solve? Well, the discussion above gives us a hint. So in fact, if there's ever a cycle, we can't do this. So that's part of it. But in general, this ranking we want corresponds to, the ranking is really in order with or satisfying I comes before j, or let's rephrase it as I comes after j. So I is greater than j means I comes before j in the ranking because we're ranking them best players first. So I comes before j in the ranking if there exists an edge I to j. So if there's an edge from I to j, we want I to be before j in the ranking because I beat that player. So this is the same as saying I is before j in the ranking because player number 1 is the best spot. Okay? So does this ordering look familiar? Well, this is exactly a topological ordering. Right? It's an ordering of the nodes so that edges always go forward in our graph. So if we had something like this, then we could have maybe 1 goes to 2, 1 goes to 3, 2 beats 4, 2 beats 3, 3 beats 4, 3 beats 5. So in this case, and let me actually rename these nodes to emphasize, maybe it's something like this. Then the ordering we want is this. This is the final ordering. And it's the same as a topological ordering of the graph, because it guarantees that players that beat everyone else become first in this graph. So that's the problem we want to solve, is finding a topological order. And in particular, you can only find a topological order if your graph G is a DAG. So G here is going to be V and E. So if our graph is a DAG, it has a topological order, and we can do this. Otherwise, we need to detect if it has a cycle and report none. So we find a topological order if exists. And so what's the algorithm? Well, we're going to use the DFS variation from the textbook that computes topological orders. But we'll also modify it slightly to say if it finds a cycle, then it'll output no ranking exists. Okay, so we can use something like DFS to compute the topological order, and also if it finds a cycle while it's doing this, because it has a back edge, it'll just print out no ranking. So this is if it finds a back edge. That's basically the cycle detection algorithm. So we're kind of combining both. Okay. Now what's the running time? The analysis. Well, this one's pretty easy. We know the running time for this algorithm for topological ordering and cycle detection is linear. It's O of V plus E. And now what's the size of V and E? Well, the size of V is just N, the number of players we had. And the size of E are the number of edges. But we know because every player, like the total number of edges possible, are going to be proportional to these rankings. So for each individual game, there's 3 possible edges that will be created due to that ranking, that game. So overall, this is going to be O of N plus 3N, which is still O of N. And this is because for each game, and there's M games. Oh, sorry, this is M, not N. So this is N plus M. So for each game, and there's N of them, there are 3 possible edges added to the graph. Okay, and that completes the first problem. So to summarize, we have all these players playing games, and we have all these little relations, these dominance relations, and we're combining them to get one total relation for the whole M gameplay. And to do this, we create this graph that models the dominance relations in all the plays, and then we notice that a cycle would cause us to not have a ranking, but actually to get a ranking, we need this topological order. If one player beat another, we have that edge, and so having an edge implies an order of the vertices, and so we need a topological order, which is only possible in a DAG, and so we also have to check for cycles. So that's the whole problem. Okay, Now let's look at another problem. So in this one, you have n galaxies connected by m teleport ways. So here already you see an n and an m. You should be thinking vertices and edges. That's kind of a hint there. M is typically used for edges and n is usually vertices. And the idea in this problem is each teleport way joins galaxies, and they can be traversed both ways because it's a teleporter. There's no reason why you could only go in one direction. But the issue with these teleport ways is if you teleport further away from where you started, there's no cost, but teleporting towards where you started is expensive. So Judy wants to take a tour of the universe, and she'll do this by starting at her home galaxy and teleporting away, but eventually she has to come back. And so to save on expenses, she wants to teleport back only once. So she's going to keep teleporting farther and farther away until eventually she takes the last edge back. And this is the problem we want to solve, the problem of helping Judy visit as many galaxies as possible. We're going to maximize her sightseeing tour. So here's just a picture of the situation. This is Judy's home. These are all galaxies. And the teleport ways are the black edge, and maybe it costs $10 to come back from this galaxy back to the home one, but the green edges indicate it's free to go farther away. So each of these is farther away, so it's free to go. But anytime you want to get closer, that's the purple edges, that will cost money. So one example of a tour that gives 3 galaxies to Judy would be to start home, move to this galaxy, move to this galaxy, and then go back. Or we could take the orange edges and keep going farther and farther away until we eventually come back. And this one will give us 4 galaxies, which is the best we can do in this problem. So that's the kind of thing we want to compute. Basically, we want to compute a max length cycle that starts at the home, which I'll call S, and each edge goes farther distance from S. So in particular, if we're at some node V, then if we move to node W, we need the distance of W to be greater than the distance of V, unless W equals S and we are coming home. So D here, that's the distance array. It models all these distances from galaxies to the home galaxy S. So that's the setup for the problem. So already it's telling us to compute the maximum number of galaxies. So this is just, like I said before, looking for max length cycles with a special property. So the special property here is a little strange. So maybe if we build a new graph, we can build that into the new graph automatically. So let's try that. So let's let V be the galaxies, just as before. In particular, these are all described by N. So numbers 1 through N. And we'll also add a special final one, T. So we want a cycle, but we don't really know how to compute cycles yet, but we know how to compute paths. We've computed shortest paths and longest paths before, so instead of a cycle, maybe we can figure out a path that turns into a cycle. So that's what T is going to be used for. we'll compute something like a path in the graph and then turn it into a cycle later. So what are the edges? Well, we'll have an edge I to j if the distance of I is greater than the distance of j. So we're just going to take this condition on the very strange kind of movements we're allowed and just build that into the graph. So in particular, we also need, there's a teleport way. Between I and j. So notice in the original, the graph is undirected, technically. But here, our graph is now directed. Because we can only move away. We can go from smaller distance to larger distance. Or this is backwards. There we go. We always move from smaller distance to larger distance. We can't go backwards. And now we're also going to add edges I to t if there's a teleport way from I to s. So this represents the final edge to go home and complete the cycle. So basically, this gives us a way to just compute a path in the graph, and it automatically tells us what the cycle is, because we always know the final edge will go to S anyway. Okay, so this is the graph, and so what's the problem we need to solve? Well, this is the longest path problem. And in particular, our goal is to compute nodes, not edges, so we're going to take the longest path and then -1. So you can put that in the problem or in the algorithm, it doesn't matter. So what's the algorithm? We use the dynamic programming longest path algorithm from the textbook. It's the same as the shortest path algorithm. So it's the same as shortest paths in DAGs, but swap the min for a max. And you can also find it in the textbook. I think it's section 6.4, around there. It's the dynamic programming on DAGs section. And so we can use this algorithm just as a black box to compute this, and then subtract 1 at the end. Or sorry, not subtract, we add 1 to the end. Well, it depends on the cases. So if there are no edges in your path, then you would add 1 because you start at home. But remember, we have a cycle, so if we ever leave H, we have to come back, so the number of edges then does equal the number of nodes. So we only subtract 1 at the end. Sorry, not subtract, but we add 1 at the end if no edges are taken. And that would only happen if there are no cycles in the entire graph. So this typically would never happen. This is just a subtle case. You don't really have to worry about it. But just something to think about. Okay, so that's the algorithm, that's the problem. So what's the analysis? Well, this is dp on a DAG. So it's going to be linear time. And in this problem, the number of vertices and edges is n plus m. Because remember, we're using the same number of nodes, just with one extra, and we're using fewer edges. We've only removed edges from the graph so that it's clearer which ones are allowed and not. So overall, number of vertices is n plus 1, and the number of edges is at most m. And then we also have the extra ones from everything to t. So that could be at most an extra n. So overall, it's O of n plus m. And you might be wondering, why is this a DAG? And that's because, so there's no cycles because we always go farther in distance. We can never go back without shrinking the distance. If we keep moving far and far to the right, distance-wise, we can never hit a cycle, except possibly at the end. But at the end, we always jump into this last node t. And so we'll never have a cycle. Visually, you could draw this as you're starting at S, you move farther and farther away, keep moving away, something like this, and then at the very end, they all have edges to the final T node. So clearly this thing doesn't have any cycles. But formally, it's because of that distance. Okay, cool. So that's a second example, an intergalactic example of how to use graph reductions.